So technology is a wonderful thing when it works. We don't have audio currently on the internet, so we're going to record this and it'll be uploaded, and the uploaded file will have the audio on it. So we'll work it out. What I'd like to do today is, first of all, talk about the project, but since there's a little more time with the seminar, I'm not going to rush through things quite so much and get into a little bigger picture, a little different picture, perhaps, than just the hard research work of it. This is part of an IDOT project. 161, also 128 is another project that was conducted here that we're going to talk about a little bit today. So we got a little disclaimer on that. First of all, I want to give you kind of an overview of recycling in Illinois. And this is important to understand what was going on a few years ago in Illinois as far as recycling and some of the things that IDOT was dealing with material-wise, because recycling has come a long way, and the main thing that was going on was we're kind of locked into this mill and fill type rehab. A lot of roads in Illinois were originally concrete, around 90-some%, and it's taken a number of years, but they're slowly getting all overlaid. So when you go back and do a rehabilitation, quite often you're doing lots of mill and fill, especially in urban areas. This was quite a problem because you've got asphalt surface out there. You really can't bury the curb and gutter, so you have to mill it out and replace it. So depending upon your percentage of recycling, there's going to be material left over. So if you're recycling at 20% or so wrapped back into it, you milled out 80% that you've got to find another use for. And that can be a problem, of course. And there's a lot of stockpiles. I'm sure here in the Champaign-Urbana area, there's also a number of stockpiles that are getting rather large. This one in the Chicago area, pretty big one. It's kind of hard to see what the real size of it is because it's about 35 feet tall, standing on top of it. So this was about a 100,000 ton stockpile of wrap back in the early 2000s. And the contractors and others, could you use the mic? Oh, we have the mic.
Yeah, it's working.
Yeah, we got the mic working now. So we'll get that on. So in the mid-2000s, IDOT was trying to deal with a lot of this reclaimed material that was stockpiling. A lot of that had to do with you need to handle the material, get it down to a size that you could use. At this time, contractors were basically sizing at one size and below. As by a crushing operation, screening, if it didn't pass the screen, it went back. So this is kind of a unit aggregate. So it's fine to maybe 1/2 inch or 5/8 size material run through there. And that's what was being done at the time. Well, as you can imagine, there's a little spots, here's a little coarser, some of it's a little more fine. So when you run this back through the plant in a mix, you have this variability between the fine and the coarse. So it doesn't control the mix real well. Out of looking at this, the adoption of what's called fractionating was done, not only in Illinois, but nationally, where you would start breaking your sieve maybe on a 3/8 inch, so you have 3/8 to 1/2, and then 3/8 and below. What does is it's like the white rock that's coming into the plant. You've sized it specifically for your mix design. This gives you some element of control in your mix. And as a result, you can increase the amount of recycling from wrap you can use in your mix because you controlled it better. You get a consistent material that way. Of course, you stockpile it and have it ready for use. Give you a little bit of history back to 2009. 2009 and 10 were what we called ARA years. That's after the 2008 economic collapse. There's a lot of public work projects. A lot of those are overlay, shovel-ready projects you might have heard of. So there's a lot of pavements built, 2009, 2010, but they were essentially low percentage of recycled material. And that's what this is showing here. How many tons per mile was being used of recycled material, whether it's HMA related, which is basically RAP, aggregate, where an aggregate could be RAP going back as an aggregate, or crushed concrete being used as an aggregate, and then concrete, which is fly ash, essentially being recycled back. So that's what these different colors represent. Other on this graph is a very small portion, things like glass beads and crumb rubber being used. So if we look at the RAP usage, like I said, 2009 was kind of a little different year because of a lot of the ARA projects out there. So it used a lot of tons, but it was at a low percentage. So the blue bars are the tons of material being used, tons of RAP, and thousands of tons. So you can see over 1 million tons of RAP was being used 2009, 2010. But the tons per mile, now this is center line miles, so you don't know if it's 2 lanes or 3 lanes or an interstate multi-lane. It's just center line miles. But on that measure, you can see that the content was fairly low. Well, about 2010-11 is when the fractionating came into play, to where we could use more RAP. Also around 2011, material called RAS, recycled asphalt shingles, came into play. And here's a stockpile of shingles, 80,000 tons, which is kind of hard to get a grasp on. Other than you see that little circle there, the line on it. That's a person. It gives you a little measure of how big these stockpiles can be. This material is used by IDOT, Tollway, City of Chicago, so a number of people are using it, and other municipalities up in the Chicago area. Illinois got legislated to use shingles back in 11, and of course IDOT follows the legislation. We allow the shingles in our mixes. So you can see 2009-10, there's a little bit of activity with shingles, but not too much. It's kind of experimental and trials and that sort of thing. Legislation 11, and then things kind of take off. It takes a little while for the contractors to react, to get their facilities lined up to accommodate the usage. But eventually, about 40,000 tons or more a year was being used in 13, 14, 15 of shingles. And the tons per mile was getting rather large too. So there's a lot of shingles being used, and the concentration of those shingles in your mix is going up. Well, that's all good and well. What this graph presents is our PG grades of our neat asphalts and our polymer asphalts. So the ones that have a very widespread are polymers. And then we have the neat asphalts, which tend to have a little less spread. So 64 minus 22 there, a little bit on the left, a couple bars in, is really a mainstay asphalt, neat asphalt for Illinois. Another one is 58-28 there on the right side. And you'll notice this one is kind of up in the air. We actually went to a shingle plant and got the liquid asphalt that they were using to make shingles, new shingles. And that graded out about 112 plus 2, which is pretty much a day like today, roughly plus 2. So the PG grades on these recycled products can be very stiff. And of course, you're putting this in a pavement and you expect that pavement to perform. So the countermeasure is to use softer asphalts in general, the best you can to countermeasure these. So that kind of gives you the basis of where things are at a few years ago, and the concern of cracking these very hard materials making their way into hot mix asphalt. And then the type of rehabs that we typically do is, like I said, we're milling off material, or we have bare concrete out there to begin with, and we're putting overlays on there, some sort of level binder, and then a surface. Surface is usually 1.5 inches or so, 1.25 inch surface, and then a level binder. So you may have had a fairly thick hot mix asphalt out there originally. You're going to mill that off and replace the new surface. binder and a surface course on it. You could have bare, or you could mill down the bare, place that new material on top. And what 10% or so roads that are full depth asphalt, those will get a mill and fill on top. And this is a very aggressive environment, especially these thin overlays on top of concrete. Here is a level binder that's only about 11 days old, and the crack has already come through. And this isn't extreme weather either. This is the end of May, first part of June, and the coldest weather you might have is a thunderstorm come through and give you a little bit of a shower. So there's not a lot of thermal movement here. This road does not have a lot of traffic, yet we've got the crack there already. So very challenging. So the focus was, how can we address this cracking, get a handle on it, where it's thermal cracking, reflective cracking, or block cracking. That's where the research comes into play. Now, I had a couple of projects. 128 was the first one to look at testing protocols to address this issue, and the placement of RAP and RAS in the mixes. Out of that came the iFit test, and this is gaining a lot of usage nationally. But that's the main focus of that study that ended in 2015. Kind of overlapping with that was this 161 study. And this was taking not only iFit, but a whole suite of tests and seeing what correlated best to the field cracking. So there's a number of interim reports, and a final report was just recently wrapped up on this. There's also a presentation, and that's the bulk of what I'm going to talk about today, that was given by Professor Akadi and Ozer at TRB. And the outline on that presentation talks about the iFit test, the protocol of credibility, the lab tests utilizing to predict the asphalt performance on a fatigue basis, and then trying to grab what data is out there available as far as fatigue tests in the field, accelerated pavement testing, and what correlation that has with laboratory tests, and then a validation or correlation with transverse cracking. And the Danes have done some good work, and looking at balanced mix designs. So some causes of the pavement distress: of course, we've got loading, we've got segregation due to paver operations, and aging and thermal loading. So the main bookends that we're looking at in pavement distress on asphalt is cracking, from loading or environment, and then rutting. Now, Marshall Thompson, with his full depth design, is pretty much taking care of subgrade rutting, so it's now confined to the asphalt layer itself, of what's going on with that mix. So it's up to the materials folks to screen out the bad actors with a suite of tests. So balanced mix design is basically, you're trying to book in these properties. You don't want it too brittle, you won't want it too flexible. Have the Goldilocks mix, if you want. Well, not too hot, not too cold. You want the one that's just right. That's the whole goal of these mix design parameters through specifications. And there's a number of ways you can get fracture in the asphalt. There's thermal cracking, block cracking, which essentially the mix is drying out and contracting. Centerline cracking can be from a few different things. Quite often that's a very low density area, and then weathering of that low density area can cause you a pretty severe crack. Reflective cracking, I showed a little bit earlier. Loading, and then top-down fatigue, or even paver segregation. So it's not a simple problem. It's pretty complex. There's all these things going on in the field: traffic, loading, temp, material properties, all play a role. And then the dollar constraint, there's only so many dollars to deal with this, both as far as what you spend on addressing the problem in materials, and in the laboratory as far as how you do your mix design and selection of materials. You can put out there a whole suite of tests to do on these mixes, but there's just not practical. The jobs need to move. It needs to be production oriented, so it has to be done quickly and cheaply. So the 128 effort was basically a whole new look at what tests were out there on the plate. The goals were to have a simple, affordable, and meaningful test. And a lot of credit to Professor Arcadi and Ozer. They went back and looked at the very fundamentals of the properties of these different types of tests, and really came out with some new thought of how to address this. So the solution was to come up with a testing scheme. Super Bay volumetrics gets you so far as a good PG grade and a good asphalt aggregate structure, and that gets you pretty far on this problem. The problem is that's pretty much for virgin aggregates, virgin mixes. So when you start bringing in all these recycled materials, where it's RAP or RAS or a combination, we don't quite know where we are at. And we get into this grade bumping situation. Well, I know it needs to be softer, I'm going to bump one grade. I know I have some very hard and lots of material coming in that's recycled, so maybe need to do a couple of bumps. So the idea was to come up with a test on the cracking side that would address this. We already had a very good handle on the rutting side with the Hamburg wheel loading test, which is a kind of torture test. It's a heated water bath, so very severe condition. It brings out mixes that would strip or those that would have aggregate structure problems. It screens those out. So the IFIT protocol is conducted at essentially room temperature, 25 degrees, and it's a quick load rate. So it's if you're into barbecue, there's two types of cooking. There's low and slow. So that's a DCT test, which is a low temperature test, and you have a very low, slow loading rate. IFIT, on the other hand, is a warm or a hotter test, hot and fast. They get you both pretty much the same place, but there's some features to the IFIT protocol that I think are very appealing and are going to gain a lot of favor nationally. The spec was published, picked up by AASHTO very quickly, actually. TP124 is the protocol. And a number of states have picked it up, and research agencies and manufacturers, of course, are always looking for new equipment to offer. And there's right now 5 manufacturers producing the IFIT devices. So the key output from the IFIT is the flexibility index. But to get there, we're going to, first of all, figure out what the work of fracture is, or the fracture energy, which is the shape of the area underneath this curve. And then the index is taking one more step further beyond that, because fracture energy can be similar even though the mixes are very different in their behavior. So here on the right we have a couple curves that the fracture energy is very similar, but you can see the curves are quite a bit different. And one has a more flexible nature to it, and the other one has a little more brittle nature to it. So how do you differentiate those and get a spread in that data? That's where this index comes into play. It takes into the slope at the inflection point there, M, in the ratio. So it kind of spreads out your data, is the purpose of that. And it helps differentiate your specimens and your mixes. Again, we talked about low and slow and hot and fast. So fracture energy at low temperature, typically you're testing at 10 degrees above the PG grade. So if you had a -22, like a 64 -22, you would test that at -12, so you bump up 10 degrees. And here we have a couple of mixes that, and this is looking at the probability of that average number. So you repeat this test, you can see one of them's a very tight band, very repeatable. The other one has a little more spread out. on the data. So that's the repeatability or probability density of this. You see there's some overlap. So what does that mean? That statistically you could end up at the same point with these two mixes, even though they're a little bit different. You bring in some other mixes and do some testing, and then we're going up in ABR. Now we're 20 versus 30% ABR. See, now that we've got 11% overlap of the data. So they're not spreading the data out with this particular test. And then if you go up to very high recycle, you get a lot of variability in the data, and as you can see, it could cross over into these the other ABR data sets too. So it is the DCT is a very repeatable test. Has a low coefficient of variation, but it just doesn't spread the data out that much. Now, if you look at the fracture energy at room temperature, you get a little more spread in the data as far as the peaks. Not as much overlap. But still, there's some overlap. So we're kind of in the middle here. Still some, you're increasing the coefficient of variation a little bit, so the repeatability might not be quite as good as the low temperature, but it has a little more discrimination. Now when you bring in the index aspect, now you're starting to spread this data apart. And that's a key component of any test, is being able to repeat it, but also being able to differentiate between groups. That's very important when you're doing production work. So the flexibility index at room temperature, it really hones in on the distribution and discrimination of different mixes. And that's what we want. If you look at it a little bit differently, a whole group of mixes, you can see that the fraction of energy alone it's kind of flat, isn't it? So it's kind of hard to, with the statistical variation, kind of hard to differentiate from one to the other. But when you bring in the index aspect of it, now you can see you're very low to very high. So you can break these apart as far as specification writing, differentiating between different mixes, good and poor performance. So now let's look at some additional laboratory correlations with beam fatigue and how IFIT, FI works with that. The fatigue that was done is a 4-point bending beam, of course an AASHTO test, 20 degrees Celsius, temp, 10 hertz, and failure is given us 50% loss of stiffness. And there's a number of strain levels being used. This is all in the data reports. To just look at a sample of that as an 800 microstrain, and you can see here's kind of a nice little spread of data. There's different mixes that was done. This is the 161 group of mixes. Different ABR levels, different RAS. Some had RAS, some did not. Percent RAP, some differences. Percent AC, and then the PG grade. And these things interact together to give you different FIs. Even though you have some hard recycled material that's being countered by soft asphalt, and maybe a little higher percent asphalt in that mix. So it's a nice flexible mix. On the other hand, you may still have somewhat of a soft asphalt, but it's a low AC content, and what recycle is in there is pretty hard material, it's RAS. And here, very good correlation between the FI and the fatigue. So good fatigue performance, high FI number. Low fatigue performance, low FI number. And then Federal Highway had some work going on doing accelerated pavement testing and looking across the country what would correlate well with their testing. course, IFIT was just coming along. And Federal Highway built a number of sections in 2015, and they were loading those about 35,000 a week. And if you ever get an opportunity to see the Federal Highway ALF or this type of machine, it's a little different than what we have here at AASHTO as far as the Atlas. It's a rail system, so it's very interesting to watch it work if you get a chance. But the objective of this study was to have a field and laboratory fatigue performance of these different AC mixes and different treatments of the mixes. And various test methods were used to evaluate the sections. So here they had a number of lanes out there. Some of them have warm mix, or a foam warm mix, or a chemical. Different ABR levels, some with RAP, some with RAS, and then a control mix. And you can see how they kind of stack out there, different PG grades. And pretty good spread in the data. So they went from about 368,000 cycles to about 23,000. So that's a pretty good spread in the data. Something to work with. So as the ABR increased, especially with harder type ABR products, the performance was worse in general. Excuse me. So looking at the ALF cycles and the flexibility index, there's a very good correlation here too. If you had a high flexibility index, it correlated very well with the number of cycles. So this is the fatigue aspect, basically. And looking at a balance mix design, 12.5 millimeters on that Hamburg wheel rut is a pretty common for whatever pass rate you need for a particular AC grade. Is different for different grades. And then the flexibility index. So the sweet spot is to have a high flexibility index, but it doesn't rut too much. So if it ruts too much, it's fail, which is the far right. And if our flexibility index is low, it's not going to be flexible, it's going to crack. So the higher upper left we can get is a better mix. How did these plot out on the Federal Highway project? They had a group down there at the lower left, you can see, and these had the less than 40,000 cycles, so those are the real poor performance. They were brittle, and they showed through that very quickly with the number of cycles to failure. Those that had a high FI had the highest amount of cycles on it. So fatigue-wise, it's a very good correlation. And there's some other tests that were correlated to the number of cycles too. Dynamic modulus, indirect tensile, and the DCT. Other than the DCT, the other ones are not correlating real well in this grouping, but by far the IFIT and the Texas overlay had very strong, very positive correlations with the performance out there in the field. And if you look at that a little bit differently with statistical groupings, which is not my strong point, but the test that has the highest discrimination potential gives you more subsets of your data. And if you look just at IFIT and the Texas overlay, you can see IFIT has a very good spread of data. We get up to 6 subsets. Texas overlay has a good spread, but only 3 subsets. Now looking at some additional field calibration validation and the 2 and 3D balance mix designs. A big thing about correlating with field data is to know what you have in the field. So you have to do a lot of detailed crack surveys. And in 161, IDOT went out annually and did very detailed crack surveys on the pavement using survey sheets and they literally walk these roads every year and map them out. This particular road on 26th Street, this is what we call a total recycled asphalt. It has a very high ABR of 60%, 4.6% RAS, and a RAP of about 51%. So when we ran the FI on this, 3.8, and it does have a PG 5228. This particular road had problems on the center line performance very, very quickly. Matter of fact, about 10 or 15% of the center line had to be milled and filled the following year because the performance was so poor along that center line joint. And some fairly wide cracks on it too. Another one is Harrison Street. Again, this is a high ABR mix. Of all the mixes we looked at in the field, this one probably had the worst performance. Also has a very low FI, about 1. And we have some other roads in here too, different FI values. And the FI does correlate very well to the width of the cracking and the extent of it. Anytime you're working with field data like crack surveys, it's very important to know what you have in the field as far as your pavement family. In this case, there was 2 basic pavement families involved. Either you had an existing section that was fairly thick. There's an old concrete down there someplace that's literally been buried by layers of asphalt over the years, and they just milled and filled off the top. So in this case, there was about 3.5 to 6 inches, depending on what section you're on, of asphalt left in place, and then the top of it was had a new overlay on it. The other detail is either you had bare concrete or it was this mill and fill concrete of the asphalt overlay on the concrete. So essentially you had a new pavement on top of an existing concrete pavement, which is, again, very challenging situation as far as reflective cracking. When you look at the crack progression of these different sections, we did see a little bit difference in the data. First of all, if you had a low FI, a lot of cracking came through over time and came through at a high severity. So you can see the ones that have 2s and 3s have a lot of cracking. There were the thin ones, the ones thick was a little thicker overlay left in place. Some other sections, these are all thin with low FI, so there's a lot of cracking that came through. And then where we had thick and thin, you can see the thick, that layer that was left in place does help on the cracking, both in the severity and the extent. And when you have thin, you tend to get a little bit more cracking, even though you might have a little higher FI on it. And this one's even a little more dramatic as far as the thick and thin aspects of the cracking. If you look at this a little bit differently, you just plot all the data up, and by season, whether it's 1 winter, 2 winters, or 3 winters, or 4, over time, you can start doing some plotting like this. And these have fairly good correlation as far as predicting how much cracking you would get depending on what FI you have. Now, IDOT has selected a minimum 8.0 as the FI that they're going, well, they actually are using it in their specifications, and this type of analysis just kind of reconfirm and reinforce that that was a good pick. It was originally picked off of the fatigue testing that Federal Highway did. This further reinforced that. Also collected in the IFIT test, the data is all there. You can also calculate what's called a secant modulus, kind of a pseudo-modulus, and add that to your 2-dimensional balanced mix design, and then end up with a 3-dimensional one. So now you've got not only your flexibility index and your Hamburg rut depth, but you could add in the secant modulus too. It just further defines what is a good flexible mix that won't give you any rutting problems. So it's just a little more definition. Whether we're ready for that, I'm not sure. The Danes have done some good work on SMAs. We're looking at mixes that would give them good rolling resistant characteristics, was their main goal. But they produced some lot different mixes than we produce here in the U.S. And they were tested a number of ways: Hamburg wheel, iFit, dynamic modulus. And you notice the curves are even a little bit differently, kind of nice, flexible, spread out. But look at these flexibility index numbers down there at the bottom, in the 30s, 40s, so very high FI numbers, exceptionally high. So you can get good high FI numbers if desired. Hamburg, some of these mixes are a little bit on the soft side. You notice that a couple of them are going off there. Illinois would drop off about 12.5 would be a failure on the rut depth. So some of these probably would not pass on the Illinois side. But the ones that did have low rutting have very good FIs. And if you look at the balanced mix design in a two-dimensional plot, you know, some of them are on that soft side. And using 10 now instead of an 8, very good crack resistance on these mixes. Now bringing the 3D element and using those newer parameters, there's basically one mix, this SMA8, falls within the boundaries of all 3 parameters. So there's some challenges, but these are very good FI numbers and a little different way of looking at the data that can be generated through the iFit test. So to conclude some remarks, fraction energy, especially at low temperature, may not distinguish between asphalt concrete mixes. iFit is the practical, affordable, reliable test to distinguish between AC mixes, and the method is being supported by both theoretical and numerical methods and extensive lab and field testing. FI is able to predict the AC potential cracking, correlates well with load testing, field cracking studies. Basically, the higher the FI, the less transverse cracking is exactly what we want. One thing to note, though, that FI, it is such a good parameter that it does pick up changes in your mix with time. So if you make a mix and store it for a period of time, it will test differently than at the time you produced it. So it's aging, and the test does pick that up. So what that brings into play is some interesting requirements on protocols of how you handle material validations and approvals between the agency and the contractors. So contractors and agencies may want to optimize AC mixes through predicting potential cracks and rutting using a two-dimensional model, which is pretty much what IDOT's doing now. We ready for 3D? I'm not sure. That might be a little bit of a stretch right now, but it's something to take a look at for the future. And we had on this study an outstanding group, a rather large group compared to some studies. Of course, Professor Akati and Ozer, and our students here, a couple of consultants, IDOT, and our Danish friends. So, thank you. Any questions, comments?
Questions?
There.
I got a couple of quick questions. First of all, the Danish samples, did they purchase the equipment and run over there, or how did they, how do we collect their data on the SMA mixes?
I'll refer to the.
We perform it. They ship us some samples.
Oh, okay.
We help them out.
Asphalt concrete?
Yeah, those are.
Oh, loose.
So they send them over, right?
The second question is, I noticed the different winters, and these were samples then taken from actually the old asphalt.
Well,
the
for
roads.
the study, the testing for the most, although there's cores taken every year, the FI test in the graph is at production. So the idea was to have a test at production would predict long-term performance. Because that's what your real opportunity is as far as a specifier working with our contractors is up front in the lab and at the plant, come up with the right mix that will perform well. So the idea was to correlate that aspect through time. So when we say one winter, that's the cracking at that particular winter, and the next one and the next one. So the FI is still the original production from the plant.
So the 4 curves that you showed, how the crack length is increasing, right?
Yeah, you get more cracking with time.
Right.
Yeah, in general.
But those are not actually cracks observed in the field, right?
Yeah, yeah.
Are they?
Oh, yeah.
They are.
Go back here.
How about the tests? The cores are taken after so many winters then, and they're tested, or?
Yeah, they were tested within weeks to a month or so after the cores were taken. That's not what this data in this graph is. This is the linear feet per 1,000 feet, so it's a unit measure, and how much cracking you have in that unit measure, and then the flexibility index. The flexibility index is at plant production, so this is within a month or so of being produced. And then the different years are just what showed up in the crack survey that year. So the first year being the blue line, you don't have too much cracking coming through. And then the dotted yellow line, I think, was the last year.
Oh, I see. Of those different mixes put down and paved,
Yeah.
these are different occurrences.
Yeah, this is
different
the
times.
same set of mixes with time. Yeah. Okay. Here are questions?
You mentioned the correlation with beam fatigue, and there's the different levels of microstrain, and I think you showed a graphic of it with the 800 microstrain. Were there comparisons at other levels of microstrain? If
Yeah,
it
that was
still
more
correlates
pronounced.
strongly?
Yeah, that was just more pronounced because it's higher level. It's in the report, so.
Maybe. Yeah, so
Maybe
we
I-
compared many level many level strains, but when you talk about so the fatigue test is a fatigue test, well the flexibility index is a fracture test, so we are not expecting them to have a complete correlation between the two, since each one is like something different than the other. But once you go above like 800, 900, you will see clear trends as it becomes more of like crack. Not a cracking, but it's closer to cracking. So you'll see this trend. There is a trend, but it's less pronounced when you are looking at low microstrain.
You will see it at the higher strain.
At higher strain, you see
You
it.
will see it because the material becomes weaker.
Here are comments or questions?
No
Or
question.
back over to you, Earl.
The cracking here in this picture is all kinds of cracks, right?
These are transverse cracks, and they could have been over a joint, could have been over a pre-existing crack, or it could be a new one in the surface. But they were showing up as far as cracking.
Just transverse.
Transverse cracking.
Could be reflective cracks. Or,
Yeah, for the most part, 95% of them are reflective cracks.
Yeah, if I may make a comment, I guess, Dave, it's interesting that all the time we're talking about cracking, if it's a reflective cracking or if it's a transverse cracking. But the matter of the truth, if you have a material that it is, or it has the ability to resist the crack or control the crack, it's going to perform accordingly, regardless of the originality of the crack. But it may take longer time to crack in one case than the other case. So I think our goal here is to try to be able to identify materials that it will resist cracking, regardless what's the original of the crack or where it's coming from, because a crack is a crack.
Any other questions, comment?
All right. All right.
Thank you so
Thank
much.
you.